Alrighty, my gremlins, we are back at it again. Okay, continuing with the example problems with that 15-minute recording time. Alright, so next problem. We have an HCFC 22 liquid line, and it is operating at 90 degrees Fahrenheit and 193 psig. And look at this. I even actually pulled in the tables for you guys. Where am I writing? Oop, there we go. Actually put on the tables for you guys. So HCFC 22, right? So we got to make sure we use the HCFC 22 tables. Okay? Like I said, pull them in for you guys. I think this is before we had the other I don't know. Either way, it is liquid, and it is operating at 90 degrees Fahrenheit and 193 psig. So a liquid line would be like coming from your condenser. Okay? Condenser going this way. Okay? Or going into your evaporator. That would be liquid lines. So we are at 90 degrees Fahrenheit, 193 psig, and we want to know the condition of the refrigerant in the line, okay? What are the three conditions we can be at? So we can be at saturation, okay? Meaning that the values on our temperature and our pressure, okay, are going to match up, right? Because this is a saturation table. All right, we can be superheated. Can a liquid be superheated though? The answer is no, right? Because if you try to superheat a vapor, try to superheat a liquid, okay, you're adding heat to it, it's just going to evaporate. And it can be subcooled, okay, meaning that for whatever pressure it's at, the temperature is going to be lower than that it would be at saturation. So let's see what we got. I already coincidentally underlined the correct one. So HCFC 22, this is the table for it. Just take my word. HCFC 22. See, there you go. All right. 90 degrees Fahrenheit, okay, is 168.4 psig. Okay, so we know that's not correct. So logic will tell us it's subcooled, okay, but let's check it out just to see. So at 193 psig, right? 193 psig, we should be at 99 degrees Fahrenheit, right? 99 degrees Fahrenheit, okay? That would be saturation. But instead, we are at 90 degrees Fahrenheit. So we are colder than we would be at that pressure at saturation. So that means we are subcooled by 9 degrees Fahrenheit. Make sense? Check it out. Bam. 9 degrees Fahrenheit subcooled. Okay, next problem. We have an ammonia vessel, and it is rated at 40 cubic feet of liquid ammonia at 80% full and 90 degrees Fahrenheit. So you have a vessel, okay, when it's 80% full, which is the max you should fill a vessel, remember? Okay, 80% full. That, I'm going to let you know, is extra information in this. Okay, so anyways, finish the question. Ammonia vessel is rated at 40 cubic feet of liquid ammonia at 80% full and 90 degrees Fahrenheit. How many pounds of liquid ammonia will it safely hold? Okay? Now, you may think you might have to do something with this 80%, but we already know that at these conditions, okay, when it is 80% full at 90 degrees Fahrenheit, it is rated to hold 40 cubic feet of liquid ammonia. So these conditions are how much it will safely hold. So we already know. So we don't technically need this. We just need to know that at 90 degrees that this vessel, okay, right now is currently the safety threshold for it is 40 cubic feet, okay, of ammonia at 90 degrees Fahrenheit. And we're trying to see how many pounds that is equal to, okay, because we already said that it is rated to hold this much. So rated, right, safely hold, same thing, okay? So it's just like the problem we had earlier. We're just moving from cubic feet to pounds at 90 degrees. I feel like I underline. I draw like all over this thing. All right, anyways, continuing. Okay, so all we have to do is take 40 cubic feet, okay, over 1, and look at that. I already put the table in here. I don't know why I did that on some of these and not the other ones. Doesn't make any sense. Either way, 40 cubic feet. So at 90 degrees Fahrenheit, right, we are looking for pounds per cubic foot, okay, because we want pounds as our units. We don't want cubic, we want to cancel out cubic feet, okay? So that is going to be pounds per cubic foot is density, all right? And this is liquid ammonia, so the density of liquid, not the density of vapor, okay, at 90 degrees is 36.98. So 36.98 pounds per cubic foot. That was the bell. You guys are fixing to be here in a minute. Okay, so cubic feet cancels out. We're left with pounds. And we need 40 times 36.98. 40 times 36.98 equals 1,479.2. So 1479.2. So 1479.2 pounds of liquid ammonia, right? So if this vessel is rated to hold 40 cubic feet of liquid ammonia at 90 degrees Fahrenheit, it is rated to hold 1,479.2 pounds of liquid ammonia at 90 degrees Fahrenheit. Okay, because those are the same. And if we look on the next page, bam, 1479.2, that is the correct answer. All right, next problem. This one says 66 PSIG and PSIA. Okay, so we have 66 PSIG, we're looking for how much that is in PSIA. Okay, we're assuming that we are operating at sea level. Ooh. Okay, so let's draw it out, all right? So we're going to have 0 PSIA, okay, a little line, and 0 PSIG is above that, okay? And in between, we have 14.7 PSIA, okay? Because PSIG zeroes out, including the atmospheric pressure, whereas PSIA absolute does not already include the atmospheric pressure, which at sea level is 14.7 PSIA. Okay, so right here, this would be equal to 14.7 PSIA. Okay, I try and draw this out every time just to kind of keep it in your head. So we are at 66 PSIG, so from PSIG, we have 66 PSIG. So now in PSIA, from the 0 point there, that was the bell song. So continuing. So this, we're looking for what this is, okay, from PSIA. So all we gotta do is add those together. So 66 plus 14.7, that's gonna be 70, 80.7. 80.7 PSIA is equal to 66 PSIG. Is that right? Yes, it is. Look at that, mental math skills. Okay, so another example problem. Look at me putting all this stuff in here. Doing great. Okay. All right, so we have an ammonia system that is operating with so it's ammonia. Looks like we have the table over here already. Operating with a suction pressure of 8 PSIG, and the suction line has a 3 PSIG pressure drop. The evaporating temperature is, that's what we're looking for. I cannot circle things very well. The evaporating temperature is, okay, so in our evaporator, we should be operating at saturation, okay? And so when we come out of our evaporator, our vapor should be at saturation. But, you know, there are pressure differences there. You know, it can gain some superheat at the end of the evaporator. But, so yeah. So let's just look at this problem. Let's draw it out. All right, so we have our evaporator, okay? And we have our compressor. All right, and now it says our suction pressure, so to our compressor, is 8 psig. Okay? And that we have in this line, our suction line right here, somewhere in that line, we have lost 3 psig. Okay? That means that our evaporating pressure, right, is going to be, since we lost 3 psig here before we got to here, right, our evaporating pressure is actually going to be 8 plus that 3 back that we lost. So 8, 9, 10, 11. So our evaporating pressure should be 11 psig, right? All right, so now that we have our evaporating pressure, it's easy to find our evaporating temperature. So we go over to our ammonia table and look, we're evaporating. It's a phase change, so we're at saturation. We can use our saturation table, and we are going to look for 11 psig. Now, it doesn't actually have 11 psig, but we have 10.82, which is the closest, okay? So, I mean, technically we could do like half degrees here, but, you know, that's not necessary. 10.82 is the closest, so our evaporating temperature is going to be -7 degrees Fahrenheit. Bam! Look, that's the right answer. Alright, gonna stop this one. I'm at like 12 minutes, so see you on the next one.